And welcome back to Flood 2000, Lesson 4, Hydraulic Valves. Valves are used, obviously, to do many functions in a hydraulic circuit. They determine which direction the fluid is going to go, how fast it's going to go, and also what pressure that the fluid is going to circulate within the system. Now, the outcomes of this session, we're going to look at the three big basic types of valves. In this first presentation, we're just going to look at the first one, pressure control valves. We're also going to look at directional control valves, which direction the fluid goes, and also flow control valves and how fast the fluid is moved around and how fast that your actuators move. Okay, so let's first review the basics here. We're going to look. This session will require you to apply some new learnings that you already know. First of all, what is pressure? Pressure is what happens when we restrict flow. Without restriction, we don't have any pressure. Some residual pressure is built up in a hydraulic system from the fact that the fluid is flowing through lines and tubes, conductors, actuators, and valves. That's residual pressure. That doesn't count that pressure that's required or the force that needs to be applied to the final load. So those parasitic pressure drops, we want to make sure we minimize those if necessary, so our pump doesn't have to work any harder than it has to, because that costs us energy. So pressure of a system affects the force. The more pressure over a certain area, the more force I have. Okay. The flow rate is how much fluid is flowing past a fixed point, and it's usually in liters per minute, liters per second, those kind of units. Flow rate affects the speed the actuator will move. How fast does the cylinder extend? How fast does the motor spin? It doesn't affect the force, which is very useful, and why hydraulic systems for the longest time were used for speed control rather than electrics, because it was so much easier to do. More flow, the actuator moves faster. Less flow, the actuator moves slower. Long story short. So what do the valves actually look like? Well, on the top left-hand corner there, you have a picture of the three basic types of valves. You have a pressure control valve on the left, and in the middle you have a directional control valve. And on the right you have a flow control, or as I like to think of it, a speed control valve. They come in all kinds of ways to actuate them. You have solenoids. They can be controlled by the actual fluid pressure, called pilot valves, and they can be controlled manually by an operator, a manual input. So the first thing we want to talk about with valves that can be confusing is this concept of normally closed and normally open, NC/NO. If the fluid will flow through the valve at rest, in other words, without it being actuated, then it is said to have normally open. If it doesn't, it's normally closed. Normally open valves do allow fluid to flow in their deactivated, but as the valve works, it will then shift or cut off the flow. Normally closed valves do not allow fluid to flow in their normal state, but as the valve starts to work, it does allow the fluid to flow. If you're familiar with electrical technology, my apologies. Normally closed in electrical schematics is the opposite of a fluid system. It's just something you're going to have to get your head around. It takes a little while. What I find helps is following the arrows. For instance, in this one down in the bottom right-hand corner here, I have a two-way solenoid valve, and it's normally open. The reason I know that is because there's a straight line of fluid to flow through. Okay, when I energize the solenoid coil here, it will switch states, and both of the inlet and the outlet will be plugged. When I de-energize the coil, the return spring will return it to its at-rest position, which is normally open. Right? Okay, now we're going to talk in this presentation about pressure control, and that's a central feature of any hydraulic circuit. You want to be able to limit your maximum pressure for safety reason, reduce the working pressure so you don't use any more energy than necessary. You may want to alternate pressure in different steps of a process. For instance, if you're making tubular metal chairs and you have to pinch the metal, bend the metal, and drill the metal, that may take 3 different units of force. As a result of that, you're going to need a different type of valve that can reduce the working pressure. You will also need to have some kind of a way of sequencing it, and we do what I call a sequencing valve, where one circuit has to work before the second circuit has to work before the third circuit has to work. Counterbalance valves are kind of a way of a system check to make sure that the system doesn't overdrive in one direction, a motor doesn't run too fast, it has braking elements in it. It's quite an interesting circuit and has various applications. This is the simplest maximum pressure relief valve, or PRV as most people call it. These valves are used for 2 main purposes. They're used to regulate system working pressure, and they can be used as a safety valve that dumps pressure if a malfunction occurs. This is the simplest type. This one has a pilot line coming back to the pump. These valves are often adjustable, as indicated by the arrow up here on top of the spring on the schematic symbol. But extreme caution has to be taken with these. They are set to system pressure. They're a safety device, so you really don't want to control operation with a PRV unless it's a very simple system. So pressure relief terminology that you'll have to get familiar with: cracking pressure, full flow pressure, and pressure override. Now, this poppet valve here has an orifice with a plug in it. The plug is a cone shape. As a result of that, the pressure or the fluid hitting this surface area encounters a fairly large surface area, and since it's basically fluid at rest, it's not moving, it's under Pascal's law. So the pressure is the same throughout the system here. Once it overcomes the spring pressure here, it will allow some fluid to go past. That's what's called cracking pressure, because you have a fully extended spring, a large surface area on the poppet, and the orifice is totally plugged. It doesn't take much to get it off. However, full flow pressure is a totally different story. Because a spring works using Hooke's law, which means that the more you push on a spring, the harder it pushes against you, i.e. negative feedback. What happens is, as the pressure comes through here and pushes this poppet off the orifice, it now hits a smaller surface area. So if the pressure remains the same, this will just seat itself. In order to blow it wide open and keep it open, it requires more pressure. The difference between the full flow pressure and the cracking pressure is called the pressure override, right? And you want to keep that as low as possible. So this is a simple PRV, and you have your normally closed valve. So this is normally closed against that surface there. And as the pump builds up to 1,000 PSI in this case, it will start to crack some pressure off. I can adjust the pressure on this spring by preloading this handle on this helical screw here. The harder I screw this in, the more pressure this spring is under, and the higher the cracking pressure and full flow pressure will be required to make this valve operate. Okay. Now here's a little graphics image file that shows you how the system works. You have the spring force pushing down and the full valve relief pressure pushing up. Now on this one is a ball valve, same kind of idea as the poppet. Ball valves are used generally on very low system pressures, simple systems, ball bearing on a spring, similar to a check valve. Once you overcome that, it allows it to flow. I think of them as check valves with really, really tough springs in them. Okay, so a pilot operated relief is a little bit, well, it's what's used in most cases. The difference between a pilot operated relief and a direct acting pressure relief valve is you'll notice it has two springs in it, and the two springs have different functions. This spring acts very much like your simple pressure relief valve, direct acting. The difference is this. This piston here has a very light spring on it, only about 20 pounds pressure. But what makes it work is there's a small channel through this piston here that closes this valve, and that allows fluid from the pump to weep into this system here. Now, because this is 20 pounds spring pressure plus system pressure, it keeps this closed. However, if the pressure goes up anymore, it overcomes that spring pressure by popping that off the poppet there. As a result, you get a magnification effect, and you can have full flow at a lower level. That results in a lot of reduction in the amount of energy required to open that valve and keep it open, and a smoother opening and closing. So it kind of self-governs the system. That way, the system is much more efficient, and you don't have the chattering of the valve so much. Now, you'll notice again that there are two sections of this valve. There's your sensing line, which is your red, and then you have your main flow circuit, which is your blue. And this is the light spring here, and this is the heavy spring, similar to direct acting. And this is my little orifice that allows some fluid to come through here and actually move this poppet. So if this comes back, if this is set for 1,000 pounds or 100 bar, let's say, it will take 120 bar to crack that open. But once that's alleviated, then the full flow pressure is easier to maintain. The difference between the operating pressure and the cracking pressure can be reduced significantly at that point. So for instance, if I have a system that has a pressure relief valve set at 100 bar and full flow pressure through that pressure relief valve is 150 bar, I have a 50% pressure override. This valve allows us, with the internal pilot mechanism, to reduce that to as little as 5% pressure override, which significantly reduces the amount of energy required to pump the fluid around the system. Okay, other types of valves we can use are unloading valves. Unloading valves are, as the name implies, they unload a system when it's not in use, or they allow the system to carry through on the pressure that's already built up. And then that way the pump can reduce its amount of output while the system is charged and ready to go, but not doing anything. So in this circuit, there's an accumulator on the top of the circuit, and this is a dead weight accumulator here. And what an accumulator does is it acts very similar to a capacitor in an electric circuit, and we'll have an entire presentation on accumulators coming up next episode. Okay. An accumulator acts as a power storage device, and it has a bladder of gas inside, sometimes a spring, sometimes a dead weight. There are different types. So accumulators can be used for two purposes: to supplement the flow rate of the pump during peak demands, and to act as an emergency backup power supply in the case of a power failure. So if, for instance, in a wind turbine, we'll use unloading valves and accumulators on the blades. Wind turbines need to be connected to a functioning grid in order to work. Otherwise, they will run away. The way you prevent them from running away is, of course, apply brakes, but the easier way is to take your blades out of the wind. So upon a loss of power in a wind turbine, the blades will turn 90 degrees and turn themselves out of the wind. This is done by accumulators because those blades are positioned by big hydraulic cylinders. Okay, so in this circuit here to the right, a common pilot operated relief valve is used as an unloading valve. The purpose of it is to unload the pump when it is not needed. That is to allow the pump to remain pumping fluid, but not restricted, causing pressure to build, which is what takes your energy. So I can continue to move my fluid around my circuit, filter it, keep it at the right viscosity, what have you, with a reduced energy load on my pump. Okay. When the accumulator is charged, the pilot line senses this and allows the unloading valve to open, allowing the pump to remain running but not under load. So here we see that the pilot line is on the accumulator end. As the pump pumps fluid through this check valve, it charges the entire system and the accumulator up. Once it's up to its pressure that it wants to have, I can just use the PRV to unload my relief valve. Right, sorry, use my PRV to unload the system. Quite simple. Used a lot. So this is an example of an unloading valve here. They look very similar to a PRV. On the top picture, you see the unloading valve is closed, causing the pressure to build up. On the bottom, you see the pilot line sensing high pressure in the accumulator circuit and causing the relief valve to open, lowering consumption. And again, notice that check valve that backflow to the pump and keeping the system charged on this end. So this is an isolating device here. Now the difference here is you'll see that you have a nice flat disc on this side and you have a poppet cone on this side. This prevents a lot less surface area than this does. And with the same force, of course, this will help push it closed. If this comes this way, it will open it up, right? So the sensing circuit having the two different surface areas allows that to happen. So pressure reducing valves here. The purpose of this one is to lower the pressure to one part of the circuit to below the maximum of the pressure relief valve. No valve senses pressure going through the valve. The valve starts to close as preset pressure is reached. This prevents the fluid flow from entering the cylinder and increasing the pressure there. So as we come through here, let's pull it out of the pump. Pump comes through here. This is our maximum pressure relief valve for the whole system. This is pumping against a closed directional control valve. More on these in the next presentation. If I activate the solenoid and move it to this position, that will allow pressure to go this way. Right? As the pressure goes this way, the first thing it's going to do is it's going to come to this one is going to block the flow from this cylinder right here. So as the flow comes through, it can't go against the check valve. This is a normally open valve, so it starts to build pressure on this side. As this moves and pinches against the piece here, the pressure will rise once it's pushing against resistance. That will allow fluid to come back through the pilot line and close the valve. Any extra fluid will get pumped through the check valve. So this will maintain a pressure on this. That then allows the pressure to build in this system here. And once it's switched over, this can then go to the second operation. Right? So this will be a sequence operation here. But this requires different pressure than that requires. So we'll use our pressure reducing valve here to accomplish that. Okay. Next up, we have a sequencing valve, which is similar. The purpose is to cause things to happen sequentially, like one thing after another. Notice pilot passage that helps shift the valve once high pressure occurs on full extension of the clamp cylinder. So we have cylinder 1, cylinder 2 here, and we have a clamp cylinder. So once the clamp cylinder pressure comes out of the pump, goes into here, through these holes here into my clamp cylinder. Cylinder reaches its maximum, it pushes against the spring, which then allows fluid to flow from here and goes down to my punch cylinder. So unless this is maintained and has sufficient pressure to push against this spring to allow flow through to the second cylinder, it won't do it. Also, we have to vent this back down to the tank, the pilot line. The sequence valve, it's very important on sequencer valves and counterbalance valves that this line to the tank is kept open and free of dirt, which is why it's important to have very clean fluid. The passageways can be very intricate and very small, and it doesn't take much of a piece of dirt to clog that up and really mess up the operation of this. So sequencer valves, again, are using pressure to have one thing happen after the other. Okay. All right. So those are the basic types of valves that I wanted to cover with you on the pressure side. So again, there'll be a few notes attached to this lesson that you can review, as well as some links to videos that you may be able to get. Okay. Thanks a lot, and we will see you next time when we're going to talk about directional control valves.